onto V. And there is a formula for this, which I don't have, so I'm gonna go look for it. What does start, I believe part of it does start with the dot product. Let me see if I can find this. I don't know if you have it handy or not. Oh. Images. Okay, there it is. So the formula is it's U dot V over the magnitude of V squared times the vector V itself.
Okay.
And your book may have a similar formula, but that's roughly it. So we got to first find the dot product. U dot V is 3 times -2 plus -7 times -6. So that's -6 minus 42. So that's -48. The magnitude of V is -2 squared. You take each component and square it. And then you take the square root of it. But since you're squaring it, you just square that. So you basically just square each part and add. So that's 4 and 36, that's 40. So it's like this. U dot V is -48 over 40 times the vector V, like that.
Got it.
So 8 over 40 to 40, they both go, both are by 8. So that becomes -6/5, -6/5 times each of these. So you end up getting -12/5, comma 36/5. Something like that. 28 is exactly the same, just different numbers. The projection is physically kind of has an important meaning. It's like how much of one vector is in the direction of the other, which is what this is trying to express here. So again, you need to first find the dot product. -2 times 9 plus 8 times -3 minus 18 minus 24, so -42. And then you need the magnitude of V squared. So it's 9 squared plus -3 squared, 81 plus 9, so you get 90. So that's -42 over 90 times 9 comma -3. Ooh, let's see here. I know 3 goes into both of these. What's that get? That gets you down to -14 over 27, I guess. Actually 6 goes into both. So you get -7 over 15 times 9 comma -3, -63 over 15 comma 21 over 15. These both also reduce, so I guess you got to do that as well. I wonder if the previous one did not reduce. Okay, so if if you're allowed to use a calculator, which I assume you are, you should definitely just make sure you get your fractions right. -21 over 5 comma 7 over 5, like that.
Got it.
So that formula is very important if you're going to be asked to do these on a test or a quiz. 47 is the next problem that I'm seeing. Story problem. Okay. This is a physics problem in a math class. If you had physics, you may have already seen this. All right, so a 2,000-pound car is parked on a street that makes an angle of 12 degrees with the horizontal. Find the magnitude of the force required to keep the car from rolling down the hill. Okay, so this car has a force going straight down like this, and it's actually probably easier if I draw it over here, kind of more. So there's usually it's represented as a box. So this force going straight down is actually broken up into a component this way and this way. And you change your axes into this X and this Y, you kind of rotate them. If you haven't seen this before, it's pretty, you just follow the example if you get more on an exam. Theta is matched here. This angle is the same as this angle. Okay, so the weight, this 2000 is the hypotenuse of the triangle. So to find the y component here, the y component is the 2000 cosine 12, and the x component is 2000 sine 12. Now normally they're flipped. Usually x is cosine and y is sine.
Yeah.
Okay. So the force required to keep the car from rolling down the hill is the one that's in the x direction. So it's this one. You just have to calculate that. Okay, part B. Part B is just finding the other one, the y value. So basically just got to find both of these. And your answer is in pounds. Let me get these for you in case you want to compare your answers. So format one. Okay, so the y value is 1956 pounds. And the x value, it's gonna be much smaller. It's 416 pounds.
Okay.
And I guess I guess maybe if you've been driving for a while on a street with a hill, you know, that doesn't take as much force as you think to keep the car from rolling.
Yeah.
Although 400 pounds is I don't know, it's a lot of. I mean, you could probably push 400 pounds if you had to keep a car from rolling back. All right, 52 here, work. 52 work, find the work done. Okay, so the force, I'm sorry, the work is a dot product of force and distance. Let's see here. The force, though, is moving in the direction. So the force, let me draw a small picture here. There's 4, there's 5. So the force is going like that. And you want to move something along here. You want to move something this way. So we need the well, there's a lot of, I guess they go FD cosine theta. Maybe that's how you saw it in your book. I really don't know what you were given. But we have to find the F in the direction that you're moving it.
Yeah.
So the distance is 5 because you're moving at 5 units. The force is 24. So this cosine of theta comes from realizing, okay, that's 4, that's 5. If you want to find cosine of theta, the hypotenuse here, well, we can use tangent. So tangent of theta is 5/4. So theta is tan inverse of 5/4. So you can get that number, and that is your theta there. There's a few ways to do this. without maybe making it super complicated. Let me get this number here. Let's see here, E theta is, so the angle is 51.3 degrees.
Okay.
So 24 times 5 times cosine of that angle is 70, we'll say 75 pounds. No, I'm sorry, it's work, so it's not in pounds. It's work is in it's a unit of energy, it's joules.
Oh, all right.
Small thing there, may not even matter. Okay, that takes care of page 473. Page 482. It
Mhm.
says 1 through 6, no calculator.
Yeah.
And then 11, whatever, it says you can use your, you can add your graph if you want. So Desmos has a parametric. Is this just parametric that you're doing here? Yeah, it looks like it.
Yeah. Yeah.
Let me see if I can find that. Desmos, because I think we're still going to use it even though it says like not to. Let me put that in the chat here.
Okay. Thanks.
Okay, so number one is matching graphs. Okay, I think 1, 2, 3, 4. Yeah, all right. Like, you know, this is really hard to do without software. Like you would have almost no shot to do this because you have to either convert it to rectangular and then know what it looks like when it's rectangular. So the graphing really helps here. Like you're just supposed to match the graph. Now, what you could do is like see how 3 of the 4 start at 0. So
Mhm.
you could put 0 into each of these and see which one doesn't start at 0.
Oh, okay.
Well, or does not contain the point. Sorry, but even that wouldn't be very helpful because it may offset. Okay, we should just graph these. So if you have that link open that I sent you, have you used this one before, or is it something different that you've used?
I've used something different.
Okay, well, let me see what to suggest here.
Yeah,
Do you know which one you've used?
I can try and find it. Like, I know we did it on Desmos, but it just like,
Yeah, this one's different. The reason I'm sharing my screen now, the reason I like this one is, actually, this will be kind of a pain. I'm going to graph the second one. 3 cosine t, and then sine 2t. Okay, so if you're seeing my screen, what you notice is one of the things I like about this one is it kind of shows you where it starts
mhm.
by if you make the t 0 to a small number, you can kind of see that it's moving to the left. Change that to 2, change it to 3, change it to 4, change it to 5. You can kind of see what's going on there. You can see that when you go to 2 pi, it's the I don't know what to call that. It's like a ribbon bow thing.
Yeah.
So letter D is number 2. And this is how I would do it. Now, did you happen to find the one that you're
No, still looking.
let's see here. So all I did was a quick search. maybe this is it. Okay, this is probably the one you're used to using. This is probably what you saw. So let me graph the first one here. 4 cosine, oops. 4 cosine. I don't know if it likes powers of 3t. It doesn't. So I've noticed that it doesn't like powers of 3. So you have to actually change it to a power of 2 times a power of 1.
Mhm.
You get it? And then y is the same thing, although that was 4. It was 4 there, wasn't it? 4 cosine squared t, and then 2 sine squared t sine t. Okay, so this one you can see is that kind of I don't know what to call it, like a maybe a kite kind of thing. Now, if you play this thing, I think is trying to show you the direction, although I would probably have you start at 0 because there's a path. Like there's a path that you're supposed to
Oh, cool.
but anyway, so that was number 1. So number 1 is graph B. And then we could pick the one we want to do next. I'll just do 3. Actually, I'll do 4 because 4 is less typing. Sine t minus t cosine t. And then the other one is cosine t plus t sine t. And something's weird here. Sine t minus t cosine t. Oh, I see it. So I have this going, I don't know, somehow it's like going too far, but you can see it's no, that's not right. X sine t minus t cosine t plus t sine t. Weird. I'm gonna go to this other one.
Okay.
Did I miss something here? Sine t cosine t plus t sine t.
Yeah, I mean that's what it
Looks
said.
like. Yeah. So if I go to 8 pi though, so that's what's weird about the one that you are using doesn't seem to handle some of this well.
Yeah.
Maybe because it needs to start at 0. There it is. So that would do it. You'd have to know to change this
Yeah.
and so on. So number 4 is that spiral, and
Mm-hmm.
therefore number 3 is letter A. So I've got that on the other screen here. Let me go share it. I marked that up for you. I would definitely graph all these. I mean,
Yeah.
unless you're gonna take a lot more serious math, you probably this is just like a one-time thing. You'll see it. And so okay, now 5 and 6. I guess we can do 5 and 6. They're not bad.
Okay.
So they give you X and they give you Y, and they're in terms of T. So you're taking this T value and just plugging it in for X, and then you're plugging it in for Y. You're just putting those values in the table. And then to create a graph, I would just graph it in Desmos, and I will do that and snip it in so that you can see it here. But let me get some of these points here. So T is -2. Okay, and X is T plus 2. And your Y is 1 plus 3 over T. So I get X is 0, 1, 2, 3, 4. And then let me change this to like minus 1/2, minus 2. This is undefined because I think you divide by 0 there. Yep. 4, and then 5/2. And then in terms of like what the graph looks like, look for that here. T plus 2, 1 plus 3 over t. We're starting at minus 2 to 2. Interesting. Okay. So the graph here, there's an issue at 2, but you can see that this other one actually goes down like this, and then the other one goes like that. And you need these arrows to indicate the direction that it's going.
Mm-hmm. Got it.
All right, so number 6 is the same way. Although 6 we kind of actually already know what it is. It's a circle.
Yeah.
And you've probably seen where x is cosine and y is sine. So these are just the unit circle values. So x starts at 1, goes to 0, minus 1 goes to 0, goes back to 1. Y is 0, then it goes to 1, then it goes to 0, then it goes to minus 1 and back to 0. And this is again it's just one unit circle.
Right.
Like that.
Okay. So.
All right, so we can go to 11 now, I guess.
Yeah.
11. Okay, so the general strategy here is to solve the x equation for t. So that's this one over here. So t is x minus 1. And then you substitute that back into the other. So this becomes y equals x minus 1. And that's relatively straightforward. They do get more difficult, but that's your starter question.
Yeah.
We're going 13 now. Okay, so the you're supposed to put these t values into x when they give them to you like this. So this would be x equals 2 times 3 minus 3, which is 3. And then putting the other one in, you would get x equals 2 times 5 minus 3, which is 7. And that gives you the x values now that are okay. And if you hadn't seen that in class, I mean, it's not like really important, but it's something that this problem is emphasizing.
Yeah.
So again, this equation, you have to solve for t. So t equals x plus 3 divided by 2. And that goes into t in the other equation. So your y is equal to 9 minus 4, x plus 3 over 2. Okay, so that's this 4 and this 2 make 2. So it's 9 minus 2x, because you're distributing in, minus 2 times 3 minus 6. So it's 3 minus 2x, but it's only good from 3 to 7.
Okay. Yeah, these are pretty straightforward.
They do get more difficult depending on this problem here. What's your next one that you got here? 14, 15. Okay. Okay, so you can do 14 on your own pretty easily. 15, we can always come back
Okay.
in case, but there's always exceptions to the rule. This is one of them. It's if you take this first equation and you try to solve for t, you get t equals plus or minus square root of x, and you don't know plus or minus, like you don't know which one it is. You know, you could pick one, but that would be wrong. And if you want more explanation on that, I can give it to you, but I don't recommend that. The exception here is that you solve this one you solve for t in this one.
Yeah.
Okay, so t is y minus 1, and then that's what goes into this other equation. So x equals y minus 1 squared, and this is done. This is totally correct. You may not like it, but it's completely correct. It's a sideways parabola
Yeah.
that 2, 4 like that. It looks like this.
Yep.
So 14, 15, 21.
21.
21's the same as the ones we've done. Let me skip past that to 23. 23 is different.
Okay.
So the just like when we're doing polar, there's some stuff here like sine squared x plus cosine squared x equals 1. This is an identity. And the x could be anything. It could be a theta, it could be a theta, as long as they're the same. That's, and in this case, it's t. So sine squared t plus cosine squared t equals 1. So this is x over 5 equals cosine t, y over 5 equals sine t. And if you square both sides, you get x squared over 25 equals cosine squared t, y squared over 25 equals sine squared t. And instead of sine squared t and cosine squared t, if you put the left sides in, you get y squared over 25 plus x squared over 25 equals 1. And then if you clear both sides, you get, and rearrange a little bit, you get x squared plus y squared equals 25, which is a circle of radius 5.
Okay. All right, got it. Okay. We're on 25. I think.
Yes, 25. So same deal. This one's got a small wrinkle with the bounds
Yeah.
there. So there's a couple ways to do this. One is to put the x bounds in or the t in to both x and y, which we did before. This is the same style of problem that was the last one. We're gonna get a circle again, but there's a small exception here. So it's y squared over 4 equals sine squared x squared over 4, y squared over 4 equals cosine squared. So you ultimately get, because you're using the sine squared t plus cosine squared t equals 1, you get y squared over 4 plus y squared over, why do I keep doing that? It's x. equals 1. So you get x squared plus y squared equals 4. But you have to account for this right here. So how much of the circle do you get if you can only go from 0 to 3 pi? Well, this is 0 to pi. This is, I'm sorry, 0 to pi over 2. This is 0 to pi. And then this is 0 to 3 pi over 2. So even though this is the correct answer, it's only this much of the circle.
Oh.
And like if you're drawing that, your instructor would mark you wrong if you didn't, say, hey, this is where it ends.
Yeah. Okay. All right. Now 37.
All right, 37. Next page. A story problem. All right, so it looks like I'll have to share that other window.
Okay.
I think. Let me look at it a little bit closer here. Ben can sprint at the rate of 24 feet per second. So that's 24. So that's Ben. Jerry is 20. Ben gives Jerry a 10-foot head start. Here are the, so find a viewing window to simulate a 100-yard dash. So how do they do it this way? Y1 equals 3. Okay. Let me just go to that other window.
Okay.
Maybe something will stand out to me when we graph it. I prefer this one. It's got less stuff going on. So this is 20t, comma 3. And you're going from 0 to 0 to so I didn't, let me go back and show the other screen, I guess. I'll come back to this one in a moment. So the person runs for 20 feet per second. So if you're trying to get to 100 yards, 100 yards is really 300 feet. So that means that this person is running for 15 seconds.
Yeah.
And similarly, you got kind of this situation over here. So we got to at least go roughly 15 seconds, maybe more.
Okay.
So when I go back to the screen, that's how I'm going to know some of these numbers. So it's 0 to 15. Okay. And why is this thing graph? Oh, 300. Okay, let me change the viewing window. 0 to 300. Okay, so see how that's where they get 100 meters. And then the other person, I should be able to just copy all this. Yeah, so the other person is 24t minus 10, comma 5, but they're also going for some amount of time. Now notice if they go the full 15 seconds, they're going to go a lot further. Like they're going 350 seconds.
Yeah.
So what I see is that we really need to figure out when the second person is going to reach 300 feet. Or Jerry, when Ben will reach 300 feet. Because the race, well, I guess the other person will keep going. Maybe that's why your instructor wanted you to use this one. They both start at 0. Let's give me a head start. Let me check the internet here to see if there's something I'm not getting that I think we have it. I do think this is right. It's the window. The window is the other person though stops before 12 seconds. Like they stop, I don't know, 12. No, sorry, that was right. 15. They stop at they stop whenever they're done the race.
Mhm.
Wherever 310 divided by 24 is. So like, but what this isn't showing, what this picture isn't showing, that they've one person eventually catches up.
Yeah.
Which is kind of like, that's kind of what you want to see. So if this is 10 t squared, 10x squared, yeah, that's not going to help. Okay. I think your instructor's just looking for some sort of viewing window like this. It has to go out to 300 because that's the that's where they both stop. 300 feet, that's 100 yards. And the other person gives him a 10-foot head start. So in some ways, like that's what they're trying to show here, is like he actually runs further though. So it's weird. It's like, well, does he run 100 yards? I don't know. I would just put something like this down and I'll snip it in
Yeah.
and
Okay.
see if that's enough here.
Okay. Um, so I think we're on 38 now.
Here. So what I didn't do, let me do the next part. It said who is ahead after 3 seconds. Let me share the screen. So after 3 seconds, when t equals 3, Jerry goes 20 times 3, which is 60. And Ben is 24 times 3 minus 10. So that's 62. So it looks like Ben is ahead by 2 feet.
Okay. Got it.
All right, so then 38 is similar. It's kind of the same deal here. I don't know why you get 2 of these, but you do. 38. So they just want you to graph these two functions, but you got to find the right window here. Faster runner, however, hesitates. So my guess is they'll intersect somewhere. We'll do another graphing on this and see if. Let me try the other one here. Maybe this one is better graphing for what we're trying to do. 10 t minus 0.1, and then y is always 3. Okay, and then this is the graph of it. See how far this goes out. So that's way too big. 10 seconds. Yeah, 10 seconds gets you to about 100-ish. Go 11. Okay. And then I guess we have to graph another one of these.
Yeah.
I mean, that's the problem with this one, is it doesn't really allow you to do that. Okay, let me go back to the other one because I'm not seeing anything advantageous about this one.
Okay.
And then this is 100 minus 90. And we'll go out to 11. It's 3 again. So like what we're looking for, see what this one doesn't give you is the like, and I guess that's what this other one gives you is it kind of shows you the trajectories of each.
Mhm.
So you would see when they intersect, but we're not getting that on here. So the second graph would have like another thing coming towards it, and you would see where they hit.
Yeah.
So what I would do is I would just show this, but show that the arrows are going towards each other. So I guess I'll snip that in.
Okay.
Be sure that I would show, you know, like one going each direction. And then we can, maybe the next question's a little bit more, who captures the flag and by how many feet? So, oh, it's like who gets to the 50 first.
Yeah.
So you basically just set each equation 10 t minus 0.1 equals 50, and then solve this. So you get t equals 5.1 seconds. And then the other one, 100 minus 9t equals 50. You end up getting t equals 5 seconds when you solve for that one there. No, 50 divided by 9, whatever that is. So we just got to check that. 5.6. So it looks like this is part B. Looks like they get it first because they get there sooner.
Okay.
So if we were to go back to that graph, that actually does help to answer the graph here. It's not it's like 5.1 and 5.1. We can see who actually gets to 50 first. And you
Mhm.
can see that one on the left is going to get to 50.
Okay.
All right, we got enough time here to probably finish up another question. Let's do
Okay.
that real quick. 39, another
Yeah.
one. 39. Parametric equations. Okay. Are you seeing, what are you seeing right now? You're seeing that. Okay. So 39, 39, right? 39A. So it starts at 1,000 feet and it drops by 32 t squared because the acceleration is 32 feet per second squared on this type of problem. And that's actually your y direction. Your x direction is always the same because it drops straight down. So part B is just to show what happens in the first 0 less than or equal to less than or equal to 6, and you're going to show going from here to there. And then part C, it says, well, what happens when t equals 4? Maybe this is 16 feet per second. Oh yeah, it's acceleration divided by 2. Sorry, so it's 16. But then you square it. Huh. Oh, it's 1,000. Is it 32? What's acceleration due to gravity in feet per second? Feet per second. 32. Sorry, it is 32, but you actually divide it by 2, so it is 16. So when
Okay.
t equals 4, y is 1,000 minus 16 times 4 squared. 16 times 256. It's approximately 744 feet above the ground when the parachute drops out. So this is the part B graph here.
Okay.
All right, well, that does take us to the end of our lesson for today. And thank you as always for scheduling, and look forward to helping you again for your final exam.
Okay. Thanks, Matt.
Have a great day. Bye now.